Hello. In the past few weeks I've been making quite a few changes to the Quest program, thanks to many great suggestions that many people from the NMR community have been sending me. First of all, there was a minor bug which was fixed, which sometimes didn't display certain transitions, because there was a division by 0. So that bug has since been fixed. Second of all, if I calculate a Zeeman perturbed NQR spectrum, you can see that the line shape which is predicted is not what you would expect to see for Zeeman perturbed NQR. The reason for that is that these experiments are normally performed in a coil which is parallel to the magnetic field and not perpendicular. So I've added the option to change the coil angle to parallel or any coil angle that you would like. So I can change the coil angle now for spin 3/2 to parallel. And now you can see that it predicts a Zeeman perturbed NQR line shape, where this peak is centered at the quadrupolar frequency, and the spacing between these two singularities basically tells you what the asymmetry parameter for this spin is. Additionally, you can see that we can change the scale now from frequency to chemical shift interactively, so you don't need to recalculate the spectrum every single time. I'll just open another spectrum now. So this is the bromine 79 and bromine 81 NMR spectrum of calcium bromide, which was acquired at 4.7 Tesla. And I'll just change the coil angle back to 90 degrees. And you can see that the calculated spectrum matches pretty well. All the singularities line up. However, the intensity seems to decrease relative to the simulation when you get to lower frequency. And if you notice, then the frequency at the right edge of the spectrum is nearly half of that at the higher end of the spectrum. And so you would expect to have much lower differences in Boltzmann populations for these isochromats relative to these ones. And so we've added the option to scale all the intensities relative to their differences in Boltzmann populations. And so you can go in Tools now and add Boltzmann effects. And what that will do is basically correct for these intensities by their relative Boltzmann populations. So now you can simulate a spectrum and you can see that the intensities at all frequencies match fairly well to the experimental spectrum. The option to simulate spectra for the spin of 3 has also been added, which was not previously in Quest. So as you can see, you can now simulate spectra for any spin of 3. And I'll just change the spin now back to 3/2. And so you can see now that for this spin of 3/2, you can clearly see the central transition, but it's very hard to see the satellite transition just because the central transition is so intense. And so I've added the option to scale the calculated spectrum vertically. That's in the Scale menu tab. And then you can type in a value which will be used to scale the spectrum. So if I simulate it now, you can see that the central transition is truncated, and you can clearly see the satellite transitions. Additionally, we've added this interactive tool with the cursor now. So if you put your cursor somewhere on the spectrum, you can see that the position of the cursor is marked with 2 numbers, which are the x and y coordinates. And you can use these to measure very well what the chemical shifts or frequencies and intensities for different peaks are. You can also left click on the spectrum, and by doing so, a box will be generated which you can drag. And if you left click a second time, you will zoom into that region which you highlighted, and this can be done multiple times. So you can zoom in into any region of the spectrum that you like. And to go back to the original condition, you just right click on the spectrum. So I hope that all these changes make Quest easier to use. And again, if you have any more suggestions or things that you might like to have added to Quest, just send us an email. Our email addresses are in the help file. And have a good night.